Let's continue from where we left off yesterday. We started with the ring and looked at the one ideal of the ring, which is in this case was the kernel defined by a homomorphism. And then we realized that this ideal induces equivalence classes in the ring. And now the question was that can we define another ring made of these equivalence classes. So did any of you think about it? No? What would be your guess? Can we get another ring of these equivalence classes like we got for the groups? Yes, we can actually. So here is if you define, let's say S to be this collection of equivalence classes and define operations addition and multiplication as so this is one equivalence class, this is another equivalence class, and I am defining their sum. Now, although I am using plus sign here, but it is being used in two ways. One is the plus within the ring R1, which is what is meant by this plus and this plus. And this is the addition of the equivalence classes. So you must keep this in mind while looking at such an expression. This is defined as simply C1 plus C2 plus I naught. So now both the pluses are within the ring R1. So you simply add these two elements C1 and C2, and plus I naught is whatever is the equivalence class that you get. And similarly C1 plus I naught multiplied with C2 plus I naught is defined as C1 C2 plus I naught. So this is the definition of these operations on the set S. Now we need to verify that these operations on the set S make it a ring. For that, we have to see that it is a commutative group. So let's look under addition. So firstly, the closure under addition is by definition. Two equivalence classes add to another third equivalence class. Associativity is also clear again by definition. Commutativity is clear by definition. How about identity? Well, I naught is identity. Right? Because if you add I naught to any C plus I naught, by definition we will get just C plus I naught. And the inverse, well, C plus I naught will have as inverse minus C plus I naught, whatever that equivalence class is. So every element of the ring R1 is in one of those equivalence classes. So look at whatever equivalence class the element minus C belongs to, that is same as minus C plus I naught. And then you add these two. So other properties follow. Now, for multiplication, again the closure is clear, associativity is clear, it's also commutative, so it's a commutative ring, it will be rather. The identity is the only thing one has to worry about. What is the identity? 1 plus I naught is identity. The other properties follow. The distributivity of multiplication over addition, that also follows. You see that, let's see, C1 plus I naught multiplied with C2 plus I naught plus C3 plus I naught. This is equal to and then this is same as the heart of all of this. I mean, this might appear a little strange or funny to you. The reason why all of this go through is at its core the following, that when you, let's say, look at these two equivalence classes, take any element in this equivalence class and any element in this equivalence class, add these two elements in the ring, that would belong to this equivalence class, right? C1 plus, let's say, A1 in I naught plus C2 plus A2 in I naught is same as C1 plus C2 plus A1 plus A2, and A1 plus A2 is in I naught. So clearly it belongs to this equivalence. Okay. So this addition respects the equivalence classes. Two equivalence classes whole get added and make a third equivalence class. Similarly, in the case of multiplication, when you look at C1 plus A1, C2 plus A2 here, what do you get? You get C1 C2 plus C1 A2 plus C2 A1 plus A1 A2. Now last three, they all belong to I naught. So even multiplication of equivalence classes respects this equivalence class. And that is why all these properties remaining following, very straightforward. So we do get another ring by quotienting, and then we will use a very similar terminology now for this quotienting with the ideal. R/I will represent that ring, and then it follows essentially as a corollary that if phi R1 to R2 is a homomorphism, if phi is homomorphism from R1 to R2, then if you look at range of phi, which is all elements of R1 under phi, the elements in R2 that they are mapped to, that's the range of phi. That is also a ring. You can just simply borrow this. That's a subring of R2. And this R1 quotiented with kernel of phi is isomorphic to that subring of R2. This is again exactly the same way as we did for groups. The same theorem extends here. So quotienting with ideals allows us to create new rings. Again, just as it allowed us to create new groups. So let's see some examples. So start with Z and pick an ideal of Z. Any ideal of Z is a principal ideal, which is, let's say, multiples of n. And you quotient with the ideal, principal ideal n. We get another ring. What is that ring? Yes, so this is, again, this will be all equivalence classes formed by this principal ideal n, and they will precisely be n equivalence classes. Okay, and that is simply Zn. Numbers between 0 and n, and addition, multiplication. Addition is modulo n, multiplication is modulo n. Because in that quotient ring, you see that when you, or rather I should say, quotienting by the principal ideal n is equivalent to taking numbers and operating on them and quotienting modulo n, dividing by n and taking the remainder. So this is again occurring. I mean, again for groups also we had Zn, but there only had addition modulo n there when this was the subgroup nz. Now we have an ideal which is something like has more structure, so we get actually both the operations on this ring. Okay, let's move ahead. Some other examples. What other rings have we come across? Ring of polynomials. Okay, let's look at Zx. What could be an ideal in this? Take any polynomial. Take any polynomial. Say principal ideal generated by some polynomial, and that's equal to what? See, if the polynomial p is of degree d, less than d, there is a small caveat here that it's simpler to describe if p is a monic polynomial of degree d, that is, the coefficient of x to the d is 1. If it is not 1, then it becomes slightly messy. It can still be described in exactly the same way, but with a little bit of twist. So in case it is monic, then it is simply well, coefficient will have to be integer because it's, but they will all be multiples of that. Whatever is the leading coefficient of p, I won't say there will be multiples of it. It kind of will become a little trickier to describe. There will still be integers, but one has to be a little careful when defining that. In fact, let's take an example when p is not monic. Let's think about that. That's the third example, let's say. How about Zx? And let me say divide by 2x. What is this? See, Zx contains arbitrary polynomials with integer coefficients. Whenever that integer coefficient is even, then that will be in this ideal 2x, except for degree 0 coefficient. and then we can take that out. But the remaining ones can survive. So that would mean that this is j alpha 0, j greater than or equal to 1. Is this. So you can, arbitrary degree polynomials will survive here as long as their coefficient is the terms, coefficient of a power of x, if it is 0 or 1, then it doesn't fall in this ideal generated by 2x. And so those polynomials or those higher powers of x will survive. And that is what I'm writing here. So it becomes kind of messy to describe this ring as opposed to that ring. When
higher degree, like 2x square plus 1, then it will be more complicated.
yes, it will be more complicated too. So, but as the moment it is a monic polynomial, it becomes very easy to describe. So that's one observation that we can make.
If you make for j greater than or equal to, for any one will be 1, then we can say that this is the correct expression. We put the condition that for j greater than 1, it should be either coefficient should be 0 or 1. We can put the condition that for any of the coefficient is 1, then it will not come in the form of 2x. All other will.
Any one of the coefficient. Why not all coefficients?
If like x square plus
Take a concrete example.
x square plus 2x.
Yes.
So according to what we have written, it will not come in this,
It will not come, yes.
but should come in that
No?
quotient.
Why? X square plus 2x is same as x square. Is it?
Yeah.
Yes.
If we do zx quotient x,
Is that x quotient x? Yes.
then it will become z.
That's only z, that's right. There's nothing else there. You can write that zx quotiented with x, that's simply isomorphic to z. Okay, more examples. You've seen different other types of rings as well. Yeah, we've spent quite a bit of time in this larger class of integers. So z square root of minus 5, for example. What would be an ideal there? We have seen examples of ideals as well. Of course, we can look at a principal ideal and let's say just a multiple of 2, 3, and that would probably not be as interesting. Let's see some different ideals. How about, sorry?
So 2 comma 1.
That's one possibility, yes. We can look at 2 comma 1 plus square root of minus 5. This, if you remember, is a prime ideal. What is this quotient equal to? Let's see what equivalence classes we get out of this when we quotient them. Take an arbitrary element of z a plus b square root of minus 5 is an arbitrary element of z square root of minus 5. When we quotient with this, what happens? Firstly, there is a 2 here. So if we can reduce a and b modulo 2, so we can, and with that all such multiples of 2 will go inside this ideal. So what will remain is a can be 0 or 1 and b can be 0 or 1. Only 4 possibilities are left. So there would be at most these 4 equivalence classes, no more than that 4. Okay. Further, then we have 1 plus square root of minus 5. Okay. So we can get rid of y 1 plus square root of minus 5. We can replace square root of minus 5 with minus 1. because what we can say is a plus b 1 plus square root of minus 5 minus 1, and that is a minus b plus so this goes away in the ideal. Now we are just left with the integer a minus b. Now all multiples of 2 of this will also go in the ideal. So eventually what we will be left with would be just 2 equivalence classes corresponding to number 0, which is the ideal itself, and number 1. So take a general element a plus b square root of minus 5, and I will write it as this. So I get a minus b plus b 1 plus square root of minus. This is in the ideal, and I can further write this as some residue r plus 2 alpha a minus b is an integer, so you just write it as, depending on if it is even or odd, as this form. So r is either 0 or 1. This is in the ideal, 2 alpha plus b 1 plus square root of minus 5. This belongs to the ideal. This will go to the 0. So there will be only 2 equivalence classes left, or 2 elements left in this quotient ring, which correspond to r being 0 and r being 1. So those are the 2 equivalence classes. So we get a ring with just these 2 elements, 0 and 1. And what are the operations on this ring? Well, very naturally, right? 0 plus 0 is 0, 0 plus 1 is 1, 1 times 1 is 1, and so on. So what we get really here is, this is isomorphic to Z2.
Suppose we instead of 1 plus 5, we did with 1 minus 2. Then also we'll get Z2.
Z.
But aren't these two rings different? Because
The rings are different, but they are isomorphic.
So 3 comma 1 plus 5 we will get Z3.
Let's see. Okay, let's maybe
3
work
alpha plus something and then something.
that. 3 comma 1 plus square root of minus 5. Is that? This would be yeah, they will go modulo 3. This will be isomorphic to Z3. Yes. Okay, let's look at this. Although I had initially said ignore this, but now we can come back to this and see what this means. All multiples of 2 taken out. So this will leave just 4 elements. Okay. How about the operations? This is a ring with 4 elements. What are the operations or the addition and multiplication? How do they go in this ring?
A1 plus A2 mod 2.
So addition is simply component wise, right? A1 plus A2 and B1 plus B2 mod 2. How about multiplication? See, if I write, let's say, this element as the following simpler form, 0 comma 1, that means A is 0, B is 1, plus 0 comma 1, that is 0 comma 0. What about 0 comma 1 multiplied with 0 comma 1? What is this equal to? That is square root of minus 5 multiplied with square root of minus 5. That is minus 5. minus 5 modulo 2 is 1. This is 1 0. What is this? Is 0 1. 1 0 is simply number 1. So 1 multiplied with anything is that. So this is the multiplicative identity 1 0 in the ring. 0 0 is the additive identity. And how about 1 1 multiplied with 1 1? This is 1 plus square root of minus 5 times 1 plus square root of minus 5. This is equal to 0 comma 0. So that's a funny ring. It doesn't, it looks, it's very simply defined, but suddenly you find that it's a very strange kind of a ring, which even has elements whose product or whose square is 0. Non-zero element? None? It's not integral domain, certainly not, clearly it's not integral. So it's a ring of 4 elements but with a strange structure. Okay? Any other example that you can think of? Let me go back to this. Some lectures ago I had created a new example. Continuous map. F is a set of all continuous maps from minus 1 interval to R. Let's look at that. This we have earlier seen already, that is a ring. What are ideals in this ring? Certainly, if you collect all maps which are 0 in a particular interval, that this collection certainly forms an ideal. Okay, so if you let I be the collection in a given interval. In that case, I is an ideal of F, because addition of two such maps lies in I, multiplication of such a map with any other map in F also lies in I. Now what is F quotiented with I? So you have to see what are the equivalence classes induced by this quotient. All non-zero maps in this ring. What are we get equivalence classes. Each equivalence class will contain a set of maps. What is the property of those set of maps? Equivalence classes will be of the form G plus I, where G is any map. So what is, and all maps in that equivalence class will be of the kind G plus a map in I. So what is the common property of these maps? Exactly. They, in the interval minus alpha, alpha to beta, they have exactly the same value.
This will be a constant value.
Not necessarily constant. They all take on every point between alpha and beta, they take one value. For different points within alpha and beta, the values may be different. So the function need not be constant in the interval alpha beta. They can be varying, but every function in the equivalence class has exactly the same value sequence or value series in the interval alpha beta. There will be infinitely many equivalence classes, absolutely. Each equivalence class will have infinitely many functions. So it's a very much bigger ring than we have seen so far. What it does is, this quotient thing here is doing is that it's as if you are saying as if that I'm going to focus only on the interval alpha beta, not care about outside this interval. Now give me all continuous functions which are distinct in the interval alpha beta. So the quotienting is just collecting all the functions and making equal those functions that agree on the interval alpha beta. Because for the purpose of my analysis within the interval alpha beta, those functions those functions are not distinct. They are being made the same. And then we are just look at the different behavior within the interval alpha beta. And this is a very important observation, because this allows us to, and we will see that later, to look at the functions. Firstly restrict our attention to a certain domain only, and look at the functions that behave differently within that domain. And these functions are simply obtained by a quotienting operation. Let's stay with this same example and let me define a specific map. I naught is not I naught, I should say I alpha beta. So I collect all the maps that take 0 value on these 2 points, alpha beta. They may take value 0 on other points. This is also an ideal. You agree with me? This is also an ideal. So I can consider I have quotiented this ideal. How does this ideal look? This has all the maps that take the same value on these 2 points, alpha and beta. Or rather, it collects the equivalence classes, and these are those maps which have the same value on the points alpha and beta. Okay. Now notice that I alpha beta I can write as See, this is an ideal in the ring F. All these three are ideals in the ring F. The product of I alpha. Any element of this product has the form that it's a finite sum of a map in I alpha and a map in I beta. Finite sum of products of this form, a map in I alpha and a map in I beta. So any such product of a map in I alpha and a map in I beta would be 0 on both alpha and beta. So every function, every map in this would be 0 on alpha and beta. But that only shows one way. How about taking a map which is 0 on both alpha and beta? Can I write it as product in this form?
Let it have the F.
So if a map is 0 on both alpha and beta, can I write it as a product of two continuous maps? One of them is 0 on alpha, the other is 0 on beta. That's an idea, yes. So you just write, if you look at a map F in I alpha beta, which is 0 on both alpha and beta, you write it as, let's say map is G, and look at the map square root of G. There is also 0 on both alpha and beta. It's also continuous. If G is continuous, then square root of G is also continuous. So G is square root of G times square root of G, where if F is negative, then there is a problem. True. So square root of G will not always work.
To C then.
But over R, you can do something simple enough actually. Suppose F is a map, so you have alpha here and beta here. Okay, and for F, what we know is that wherever F is coming from, F is 0 at alpha, not F, some G here. Then it just goes all over, but it stays 0 on beta, and then it again goes over. Okay? So if we define a map which is continuous, so let's say, take this simple map. This one. This may not work. Wait a minute. Okay, I think this is a very good home exercise. Instead of me doing it, let me give it to you to work out an example. It's very simple. Just you don't have to try anything complicated. Just construct. See, you have a lot of flexibility. You have to define any two maps whose product is equal to this map. One of them should vanish on alpha, other should vanish on beta. Make one of them vanish on alpha, make one of them vanish on beta, and define its value on the remaining point, so that the product is the values that you want. Okay, you just have to ensure that there is a continuity. Fine? So I'll leave it at that and have you work it out. So that's it for today.